Okay, let's start the afternoon. So we are very happy to have David from University of Valencia. And he will talk on estimates for Bochner-Riesz at the critical index. So David, please go ahead.
Yeah, thanks, Jotsaroop, and thanks for the invitation, and many apologies for not being able to join you in person in Bangalore. I wish I could be there, but a couple of things came up and I was unable to travel. So the title, the topic of my talk today is Bochner-Riesz at the critical index. And I'm going to present some new results in that context, which are joint work with Joris Roos and Andreas Seeger. And the plan for the talk, since this is quite a long talk, it's 1 hour 30 minutes. I decided to split it into two parts. The first half is going to be more like a literature review of what is known, what are the questions, and what are our new results, which fit into the context of weighted estimates and sparse bounds. And the second half is going to be about proof techniques, and I'm going to be revisiting the classical approaches for weak type estimates and how they can be turned into sparse bounds, and what was the novelty and the problems we had to overcome to obtain our result. So let's start with just introducing some notation, really, because the Bochner-Riesz multipliers is an object that I think most people in the audience is familiar with, and is given by the Fourier multiplier 1 minus modulus of psi square, and we take the positive part and we raise that to the power lambda. And I'm going to be using this notation as well to denote the operator m lambda of d. That means the Fourier multiplier operator in acting on functions f's. When lambda is equal to 0, we know that this corresponds to the disk multiplier, and then when dimensions are 2 or higher, because that's when the Bochner-Riesz are going to be interesting objects. The counterexample of Pfefferman tells us that the only possibility for lambda equal 0 is this being bounded on L2, which is the trivial bound. And lambda is quantifying smoothness. So the higher lambda is, the smoother the multiplier gets. Is the Ball multiplier starts to get regularized. And then we want to quantify LP bounds in terms of the smoothness parameter lambda. In particular, if we look at the kernel and we take the inverse Fourier transform of the power multiplier, this has these oscillatory factors. There are cos function on top, and then the denominator, it has decay when x gets large. It has decay like minus d plus 1 over 2 plus lambda. So this tells us that if lambda is greater than d minus 1 over 2, then this kernel is integrable, and LP bounds are trivial by Young's convolution inequality. So the range of interest is going to be when lambda is between 0 and d minus 1 over 2. So in this context, one can formulate the so-called Bochner-Riesz conjecture, which I'm going to state it in two ways. One is for a fixed lambda. It is expected that LP bounds for the Bochner-Riesz multiplier, they hold for P in the following range between 2d over d plus 1 plus 2 lambda and its dual exponent. And when we can also formulate it in the reverse way, that instead of fixing the lambda, we now fix the exponent p. So we fix the exponent p between 1 and 2d over d plus 1. And then we expect bounds for all lambda greater than this value over here. And when we are in the range between 2d over d plus 1 and 2, then we expect boundedness for all lambda greater than 0. I'm just restricting to p is more than 2 because the upper range will be covered by duality. So here 2d over d plus 1 is also the restriction exponent, which might be familiar to some of you. And this would be the known endpoint version. And the M4 version can be states the following: that whenever we are the P in the region between 1 and the Fourier restriction exponent, and we are at the critical index for that P, which is the conjecture is expected when lambda was strictly greater than this quantity. So the critical index is what happens when lambda equals to that value, d times 1 over p minus a half minus a half. This is the so-called critical index, and in their LP bounds, they are not expected, they are false, but it might be expected that weak type bounds will hold. So this would be the endpoint version for the Bochner-Riesz conjecture. So let's just quickly revise what is known. For d equals 2, everything in the non-endpoint case, everything is known already since the early 70s, over 50 years ago, the work of Carlos Oncholin. And for d greater or equal than 3, the problem is still open, and as many of you know, this is a big open problem in harmonic analysis. But there are partial results. The answer is yes for certain values of p, and there's an exponent which I denoted here by p current, which is the best exponent that is known where the conjecture is verified, and which is strictly currently that the 2d over d plus 1, which is the conjecture one. And I think this p current normally gets tied, and it goes in companion with the progress on Fourier restriction conjecture. And I think the current record is obtained by Guo, Wang, and Zhang only 1 year ago. But before, many people have contributed to this problem, and I've listed quite a few names here, but this list is by no means exhaustive. And there are many others that have also contribute to understanding Bochner-Riesz and to push this p current as high as possible. What is known in the I didn't write out what is the p current because that's not the purpose of the talk somehow. So what is known at the critical index for the endpoint version where weak type bounds are expected? So here, when p is equal to 1, there is this the first result was the decrease when p was equal to 1, and in that case the critical index becomes d minus 1 over 2, and our kernel then it fails to be integrable barely, right? And we expected weak type 1 bounds, and Christ actually proved that this was indeed the case. And later on, he extended this. The year here is this year goes earlier because of the publication, but really he did first the p=1, and then he extended it to a larger range. So between 1 and 2d plus 1 over d plus 3, he was also able to verify that for the corresponding critical index for that value of p, which I denoted here by lambda p, the weak type pp bounds, they also hold. And here that this exponent was excluded. This exponent is the Stein-Thomas exponent. In many times, many people are familiar with the Stein-Thomas exponent in the supercritical regime when we talk about extension operator, but this will be the dual when we talk about restriction. And this point here, the Stein-Thomas point, was later proved by Tao a few years later, almost a decade later. And all these three works, they rely on decomposing the kernel into dyadic pieces. That was the decomposition of the Bochner-Riesz multiplier that was, or Bochner-Riesz operator that was carried. It was through dyadic decompositions on the kernel side. In dimension 2, Seeger also proved, like at the same time as Tao proved this Stein-Thomas estimate, Seeger also proved the full conjecture in 2 dimensions. So he in 2 dimensions, the Bochner-Riesz conjecture is known, so then it is the only dimension in which weak type estimates for all values of P, they were at reach somehow. And he indeed proved that this was the case for all the possible range between 1 and 4/3, which this matches the restriction exponent. The weak type estimate LP to weak LP holds. And his approach was different than the previous ones in the sense that the decompositions on the Bochner-Riesz operator, they were carried on the multiplier side, more closer to the ones by Pfefferman and Cordova from a few years before that. So in that case, one decomposes the Bochner-Riesz multiplier as thin annuli that they approximate the unit sphere. So then the 2 approaches, they are somehow different in the way that the compositions are performed. And what about in higher dimensions? So of course, in higher dimensions, one cannot expect to solve the endpoint conjecture because the non-endpoint conjecture is open for generality. But one can ask whether for the piece for which the non-endpoint conjecture is known, whether we can get also the weak type result, the result. And in the range that was still open between the Stein-Thomas and restriction. And this was what Tao proved a couple of years after Seeger. He proved the following black box type result, which has the following 2 hypotheses. If we have the Bochner-Riesz conjecture in the non-endpoint situation, so strong bounds for all lambda greater than the critical index, it holds for a certain value P0, and also that the Fourier restriction conjecture for the sphere holds at the very same value P0, then the Bochner-Riesz multiplier at the critical index satisfies the corresponding weak type bound for all the P's strictly smaller than the P0 that our hypothesis was based on. So this is somehow like an epsilon removal argument in a way, combined with Calderon's decompositions. And this kind of kills off the problem because it tells us, okay, we can focus always on the non-endpoint conjecture, and whenever we have a result here, then we can get the endpoint result for free. So then the problem of the critical index was sort of resolved after Tao's contribution. Moreover, the hypothesis B is nowadays superfluous because Tao, around the same time, he also proved that A implies B. Well, not exactly. What he proved is that if the Bochner-Riesz conjecture holds at P0, then the restriction conjecture for the sphere holds for P smaller than P0, but then we would be applying this for a P as close to that we want to P0, and then we still get the same conclusion in the open range, because the conclusion is in the open P still is more than P0. So we can use this, the celebrated result of Tao that Bochner-Riesz implies restriction to get rid of the second hypothesis. So it is now really, it is now a result which really says, if you have Bochner-Riesz for the non-endpoint, then you get the endpoint. Okay. And above that estimated from Seeger, which was based on the compositions on the multiplier side, and Tao also explored it later, what they pointed out was at the following estimate. So they show that via Calderon-Zygmunt decomposition, which is natural in this weak type estimate, what it suffices to prove is the following vector valued inequality. And we are taking sums over, okay, this J should be J greater than 0. I know why there is an S, but it wasn't intended in this slide. If we can get the following multiscale or vector valued inequality that we have here, the critical index. This would be one of the Bochner-Riesz building pieces in the multiplier side. These are Fourier multipliers supported in a thin annulus, 2 to the minus j. and we put the corresponding power for the critical index, and we prove the following vector value inequality on P. If we have this can be used in a Calderon-Zygmund decomposition fashion. We'll revise how to do it later. And one can obtain the weak type results. So what Seeger did was to verify that this inequality actually holds in 2 dimensions in the whole regime. And then what Tao did was to verify when this inequality holds. And so his result is really more of the type: if the Bochner-Riesz conjecture holds away from the endpoint, then this vector value inequality holds. And once this vector value inequality holds, then Seeger's argument can be applied. So really, Tao's estimate is Bochner-Riesz self-improves to this vector value, which in turn gives you weak type results. We'll elaborate on this later. So then the problem seems kind of closed then. So what is left to study? And what's left to study are weighted estimates. And here there is this celebrated result of Vargas, which is a decreased result at the critical index for P equal 1, which is the -1/2. And she proved that weak type 1 weighted estimate, they hold for all weights in A1. And A1 is the magnitude class, which consists of all non-negative, locally integrable weights, such that the maximal function acting on the weight is almost everywhere controlled by the weight. So this class of weights is the one that characterizes L1, weak L1 weighted bondedness for the hard-deletable maximal function, and it suffices for weighted bounds for Bochner-Riesz for P equal 1 at the weighted beta bounds at P equal 1. Her approach was based on extending increased method. So it was based on kernel decompositions, and she had to use incorporate kernel size properties and a very delicate interpolation to make this argument to continue to work in this context. And then there's a natural question that now shows up, which is what happens at the critical index for when P is strictly greater than 1. Can we expect weighted bounds for some class of weights? Either magnitude weights or something else. And if in Calderon-Zygmund theory, the classical result is that the boundedness continues to happen for AP weights, which remember that AP weights are defined by the finiteness of this left-hand side. And you can think, for instance, for P equal to 2, this would be W and W minus 1, that the inequality that W times W minus 1 is equal to 1, that happens like in an average sense and uniformly over locations and scales. This is what this is telling you, but incorporated for other P's. And the classical result for Calderon-Zygmund, it cannot hold for Bochner-Riesz at the critical index. This is known that this holds in general by testing in power weights, which are positive power, and I think also by weighted weak type extrapolation theorems, it can also be ruled out. But it is conceivable that A1 will be sufficient. So let's not aim for the class AP because we know it's false, but then let's just put in the smallest possible AP class, which is A1, because the AP classes, they are all contained into one another. And thus this can we extend Vargas result in the very same class for some larger P's. And we have given some partial answer towards that question. It's not the definite answer, but what we are able to say is that for weights in A1, there exists a P, but the P depends on the weight. So it's not uniform, it's not a uniform P over the whole class. There exists a P greater than 1, such that the boundedness holds for all P's between that PW and 1. So we are extending the case P equal 1 would be Vargas result, and then we are extending that a little bit more. Unfortunately, that the exponent P depends on the weight. We cannot take. We don't know whether we can take it to be uniform in the whole class, and ideally one would like. And the reason why we have this type of theorem that there exists a P depending on the weight is because our result is really a result on weights in A1 and also belonging to certain reversal classes. So recall, this is also a standard result in weighted theory, which tells us that weights, they self-improve a little bit, these manifold classes. So whenever we are in an AP, then there exists an epsilon, depending on the weight and depending on the exponent P, such that the weight to the 1 plus epsilon, the average with the 1 plus epsilon power is controlled than the average without power. So these are all the weights satisfying these conditions. They form the so-called reversal classes with index 1 plus epsilon, and due to this, so this extra gain of the self-improvement of the manifold classes, what allows us is that from a weight in A1 we can go to a little bit more to be in some reversal class, and our result is exactly of that type. So let me state the result, for instance, in dimension 2, and I'm stating it in dimension 2 because this is where everything, the non-endpoint Bochner-Riesz is known, and the endpoint as well. And in that case, what we are obtaining is the weak type PP weighted Bochner-Riesz at the critical index. So now here I'm reshuffling the formulation, I'm fixing the lambda, and this P lambda is the critical, the one where lambda becomes critical index for that P lambda. And then here there's a parameter, sigma naught of lambda, where this parameter is the threshold for the reverse Kelder class. So I have weights in A1 intersected with reverse Kelder class sigma for sigma greater than this threshold. And in that case, we obtain the weighted weak type boundaries. And observe that this threshold here, this sigma 0, when lambda goes to 1/2. Well, remember 1/2 is the critical index for P equal 1. So when lambda gets to 1/2, then this goes 4/3 plus 2 times 1/2. This sigma goes to 1. Okay, so then due to this reason, when we have a weight in A1, then the previous lemma tells us that it is also in some reverse class, 1 plus epsilon. So because of this convergence to 1, we can always find like like that the weight self-improves to some sigma here for some lambda close enough to 1/2, and that's how we can go to the previous result. So due to this limiting argument that the threshold here goes to 1. So it is quite important here to get the right sigma 0. Okay. And the way we obtain this result is through sparse domination. This is a concept that has gained a lot of popularity in the last decade or so in harmonic analysis. And nowadays, the most standard formulation for a sparse bound is in terms of domination by bilinear forms. So we consider the operator acting on the function, and we pair it with another function, F2, and we want to control the size of that, and control it by some very simple looking object, which is just taking averages, localized averages of my two functions for two certain exponents, and summing overall cubes in some nice family. So this notation, as I was already saying in words, these brackets will mean the local average of the function with exponent p, and this one would be with exponent q prime. Q prime for now is a number. Then the reason why prime is here will become apparent in a second. And here the sum is a sum taking over a special family of cubes. And this family of cubes is going to be what is called sparse or gamma sparse. And what it means is that for all intent and purposes, they are disjoint cubes. They are not, but like a big proportion of the cube, like a subset, which I'm going to denote is a cube, which is a gamma proportion of the original cube. Those subsets, they are the ones that are disjoint. So, for example, you can think we have the following family of red cubes is sparse because the ones that we just take a cube and then we go to the dyadic children and we take that's the left, or in intervals, right? We take the left interval and then the left interval, the left interval. So whenever we do that, for instance, we have the green region here is not overlapping with the next generation. And this, if I keep getting the right hand side, it's not overlapping with the next generation, and so on. This would be an example of how one half sparse family. So this concept, which I said, it has become very popular over the last decade or so. It gained relevance after Lerner's proof for the A2 theorem for Calderon-Simon operators, which was previously proved by Hittonen, but then Lerner reproved it by means of a sparse domination inequality. And there have been many authors contributing to the subject. The question has been posed for whether these type of bounds can be obtained for several different operators. And just to name a few, important contributions have been made by Lerner, Conte Alonso and Guillermo Rey, by Michael Lacey, by Bernicov, Frey, and Peter Michel, and Cooley, Diplinio, and many more. Here, again, the list is by no means exhaustive, and there's been many other contributions by many authors. So, what is this inequality really telling us? So this is like a modern measure of size, or a refined measure of size when compared to the usual Lebesgue space bound, like a Lebesgue space estimates. So let's see what we can do with it. So once we have this inequality, we can think, as I said, that the Qs are disjoint. Not quite, but we can get the measure, replace it by the measure of the subset, which is a big proportion of it, or a gamma proportion. We miss a constant here, gamma. But now these EQ, they are the ones that are disjoint. And these averages, I can control them by the Hardy-Littlewood maximal function for all the points in the subset EQ of Q. Hardy-Littlewood with respect to power P, so taking P averages. And now, because the measure of E is as the integral over E, I can replace all that by I sum over all cubes in my sparse family, and I'm integrating the product of these two Hardy-Littlewood maximal functions associated with powers P and Q prime, and integrating over subsets EQ. They are disjoint, so I can sum over all EQs to get integration over all RD. And now I can apply Helder inequality to split the two things. Now sparse does not play a role anymore. So if I can use now I can use bounds for the Hardy-Littlewood maximal function, and in particular, this is bounded if R is strictly greater than P. and this is bounded if the R prime is really greater than the Q prime. So in other words, I end up with LR prime here if the R is between P and Q. And that's the reason why I introduced the Q prime here, so that I end up with a Q at the very end. So in a nutshell, what I said is that if we have this bilinear domination, then we have this implies in particular Lebesgue space bounds for R's between P and Q, strong bounds, and also by the weak-type properties of the maximal function, we also get at the endpoint R equal to P, we get the weak-type inequality, and at the other endpoint R equal to Q, we get the strong restricted strong type inequality from LQ1 to LQ. And what other role is the P and the Q exponent playing besides this getting bounds in this range? These are all diagonal inequalities. But the role of this secondary exponent is a little bit more than that. It's related to an off-diagonal necessary condition. So let's say that, imagine I'm going to put ourselves in a simple situation, which is going to be the one of interest for us today, in which our operator is given by an integral operator with integration against the kernel, and I'm going to localize the kernel in a spatial site. I'm going to localize it so that x minus y is about R. Okay, and I'm going to rescale that. I'm going to rescale that at unit scale, and I'm going to be considering the rescale operator. So in this situation, it can be seen, the proof is a little bit harder than the proof I showed in the previous slide, but it can be seen that a sparse bound domination inequality with exponents P and Q prime implies that the rescaled local, the local rescaled pieces, they are LP to LQ bounds. They satisfy an LP improving inequality. So then this becomes also a necessary condition on these dyadic decompositions of the kernels. Okay. And how to, as I said, how to obtain this is a little bit harder, but morally it comes from the following observation. What can we do now with this sum? Because we are not gonna, we cannot go through the maximal function to proof of diagonal bounds, right? So somehow the idea is that the left-hand side is larger than if I just had one piece, one of the rescaled pieces. That's morally the idea. And then if I just look at one, what happened when I have one of the one pieces rescaled, this decomposition is telling us that x minus 1 is about x's distance to y about 1. So the F2 and the T are rescaled at 1, the distance about 1. So we don't have to look at a small cubes contribution. We only need to look at Q and larger Q, Q about 1 and larger Qs. And then when we look at larger cubes, then there is only going to be one cube that contains both supports, because the supports are at unit scale. So then cubes that are large, they are like error terms. So then there's only one, effectively there's only one term in this sum. And when there's only one term, we can really turn this into an LP to LQ estimate. So if this is not here, this is by duality, is going to give me this LP improving. So so then these exponents, this secondary exponent is related to the LP improving bounds for the localized rescale pieces of the operator. And really what most sparse theorems are is trying to make this also a sufficient condition. The previous ones we've seen, weak type PP, the restricted strong type QQ, and this LP to LQ estimate for the local pieces. But this is not quite enough. We need to, because these only correspond to one piece, we need at some point to get some extra epsilon gain in order to sum, because there are going to be many of these R's. We can think of R into 2 to the J. We are going to need some summability into 2 to the J. So we need something extra to be able to sum and gives you a sparse bound. And normally the task is to where to get that extra gain that allows you to conclude a sparse bound. So it's close to this sufficient. That just needs this gain in a sum at some point in the argument. Okay. Also, by adapting the previous argument for diagonal bounds, one can get weighted estimates. Weighted estimates to the maximal function, so it's going to involve weights in the Markov classes, but also in the reverse-ordered classes that I introduced earlier on. So in particular, Bernikov, Frey, and Peter Michal, they prove that whenever we have a sparse domination inequality with exponents p and q prime, then we have LR bounds, weighted LR bounds with weights in the intersection of these A over RT classes and reverse-ordered with exponent q over R prime. And later on, Frey and Niraev, they prove an endpoint version of that result. So what happens when R is equal to P? Well, when R is equal to P, remember without weights, we had a weak type PP estimate. So here we're going to have a weighted weak type PP estimate. Here I'm missing the weight. Apologies. And what's the limiting class? The limiting class is R goes to P. This P over P becomes a 1. And this R here becomes a P. So this is really the endpoint version of the above. So then what we are gonna do is we are gonna prove a sparse domination result, and then we are gonna use the free Niraev proposition to deduce the weighted PP estimate in these classes. And if we get the right reverse-ordered exponent, the one that we claimed earlier on, then we can do this limiting argument and obtain the result, the extension of Vargas result for some bigger than 1. So then the focus from now on is going to be on proving a sharp endpoint sparse bound. Okay. So the way I like to see that, just as a summary after all this discussion, is that despite I presented that a bilinear estimate also implies Lebesgue space bounds, typically we need to know the Lebesgue space bounds first in order to deduce sparse bounds. So the way to see it is that we know for an operator what all the information on Lebesgue space. Then how can we go to sparse bounds? And then once we have that, we use it to deduce weighted AP estimates or AP and reverse-ordered estimates as a corollary. Okay, and we'll also draw pictures, and the pictures we are gonna draw them in the plane because of the two exponents appearing here, the P and the Q prime, and I'm gonna be drawing 1 over P and 1 over Q prime. Therefore, I'm interested between in the square, and really you can see that if this Q prime, we don't want the Q prime to be, we want boundedness in the end we want an open range between R and between P and Q. So we don't want the 1 over Q prime to be on this anti-diagonal line because that gives you nothing at the level of the sparse bounds. If we had a PP prime, then that will give you, it's bounded for all R's between P and P, strictly. That's an empty result, right? So we don't want things in the diagonal or below. And so we want to determine what is the region in this upper triangle in which we have a sparse bound and to obtain the sharp things. And the region is going to be determined by the LP-improving properties of the local single scale pieces. So let me comment on proofs for sparse domination results, and then explain what is known for Bochner-Riesz. And when there is only one single spatial scale involved in our operator, then sparse bounds are equivalent to the LP-improving bound, really equivalent. There's no need for an extra delicate argument. So let me explain that more precisely. So if imagine that we have a function which is supported. If my operator is local, there's only one special scale, as I was saying. Function supported on a cube. The cube is of size 2 to the j, and then when we run our operator tj on that function, we don't enlarge the support, so we are local at that scale. Maybe a dilate 3 times or 10 times. We don't care. And we also have that LP-LQ bounds are satisfied. And here, this is because I haven't rescaled my operator. If I were rescaling it to unit scale, this factor would disappear just by rescaling. So this factor is natural. Then I can do the following. I can consider my pairing of Tj acting on F1 localizing that cube. We have a function F1 supported there, and I pair it against F2. Thanks to the local property, the F2 also becomes localized in the dilate of the cube, because this output is localized. So I can put in a localization on the second function using the locality. And then I can use Helder to go to Q and Q prime. I can use the LP improving estimate of the shelf. And then I end up with my function F1, which is now at exponent P, my function F2, which is at exponent Q prime. Both of them are localized in Q and 3Q, and I get this factor. This factor, remember, we have that here I should have put equal, really. So this factor, it is the measure of the cube raised to this power in negative sign. So I can then distribute that to turn these two things as averages. So I just put part of it in the LP average, part of it in the Q prime average, and then there's a measure, a power 1 measure of the cube surviving. So now this, which I've done for one function localizing a cube at a scale 2 to the j, I can take any function, break it into a fixed dyadic grid of cubes of size 2 to the j. I just write F1 as a sum over all my functions with cubes with disjoint interiors at that scale, and then I apply the estimate I have on each. If my operator, I'm going to assume, is linear or sublinear at the very least, and I apply the estimate for each of the pieces, and I get the sum over all cubes at that scale. But because I'm taking all dyadic cubes at the scale, they are disjoint. In particular, they are sparse. They are better than sparse. They are disjoint. So then that gives me sparse bound. So when there's only one spatial scale, this is a very easy argument. Is basically the LP improving bound for free implies a sparse bound. So imagine that we had an extra. Imagine that now we don't have just one scale, but we have many scale, but our inequalities, they come with an extra epsilon. That would give me some ability. This very same argument, I could be summing over all positive j's if I start from j equal 0, and that would give me some ability. So, so somehow that's what happens when one looks at sparse bounds or Bochner-Riesz away from the critical index. So for Bochner-Riesz operators, this is the numbers here, they don't really matter. And let's not just focus on numerology, but let's focus on that there is a conjecture region where sparse bounds for Bochner-Riesz should hold. And this conjecture region is determined, as I elaborated on earlier, by what are the LP to LQ bounds for the local pieces for Bochner-Riesz. And that's also a problem that has been studied, and the knowledge on that tells us that this should be the region. Okay. And outside of this region, they fail, they cannot be satisfied. So in this region, let's distinguish two parts, the interior and the boundary. So the boundary given by this P1 to P2, P2 to P3, P3 to P4. And then the interior is this yellow region. So at the interior, we are not at the critical index. So then the bounds, they hold for all lambda in the open range, lambda greater than this quantity. Okay, so we are to the left 1 over p lambda. P lambda is the critical one. So once we are here for a fixed lambda, then we are greater than the p. So in that context, because of the openness of the lambda range, we get an extra 2 to the minus j epsilon as soon as we move away from the boundary. And then the previous argument applies when we localize Bochner-Riesz in physical space. Maybe there are some tails and so on, right? So one needs to be a bit careful. So it's not as straightforward as I mentioned, but the idea is more or less the same. And then the bounds on the interior of the conjecture region, then they hold from a single scale analysis whenever knowledge on Bochner-Riesz is available. And this was already observed a few years ago by Benea, Vernico, Luque, and also later on by Lacey, Mena, and Reguera, who proved the sharp bounds on the interior whenever information for Bochner-Riesz is known, if not partial results. So what happens at the endpoints? What would happen at this boundary where we are at the critical index? We cannot use the previous argument. So in that situation, we have a truly multi-scale situation for sparse bounds. And typically that is handled through a induction argument and iterate, or in other words, an iterated Calderon-Simon decomposition. So let me also elaborate a bit on that proof technique. So we'll be inducting on the number of scale. Now we don't have just a single TJ, we have a sum of them, and we'll induct in the number of terms of this sum. And the base case is just one piece, and one piece we already saw how to obtain a sparse bound. And then the induction step would be if we know it for capital N terms, can we know it for capital N plus 1? And so can we control the left-hand side by the induction, the constant at one less level, or just some other constant that we bound? And here, as I said, like this is the sort of a standard approach for proving sparse bounds for multi-scale spatial situations. One considers the usual exceptional sets for the functions f1 and f2, and then performs the Calderon-Simon decomposition adapted to the power p and q prime. Considers the union, does the Calderon-Simon decomposition for this omega, and considers the good function and the bad functions. And know that if we take, because we are going to decompose the omega into cubes, then we'll iterate the process in every of the cubes. If we take E sub q to be the complement of omega in the original q naught, then the family will be sparse. So that's guaranteed. So by doing the Calderon-Simon decomposition, everything that touches a G1, that's fine. That's easy to handle because these are functions which are in an infinity. And here we can throw in a multi-scale hypothesis of weak type or restricted strong type QQ or weak type PP, and use the infinity bound. So then let's focus what happens for the B1s, for the bad functions. And here we'd like to, there's going to be a part which is going to be proven by induction hypothesis, because these functions are localized. So then we can consider for each of W, we are going to, the part where the J goes up to the power of the side length of the W, this looks like the left-hand side, and then this can be iterated. Here we can apply induction hypothesis. Then this is when instead of B1, I have the function F1, but I'm taking out an average, right? But the average is in an infinity. So this is like the good function. So these are not the problem. So the problem would be to trying to understand what happens when I go over all W's and I look at TJs which act on these BWs, and the J is larger than the side length of the W. Okay, that's going to be the more challenging part. So here I still have a second function, so I can do again the same business: good function, bad functions. The good function can be treated, and then the goal would be to try to understand what happens if I have an interaction between bad functions and bad functions. And here is where the LP-LQ argument is not good enough. We need some extra summability. That extra summability may only be seen at this stage for a given operator, because we are going to be testing our operator against a function which are much smaller localization than the locality of this operator. So maybe we are going to be able to gain the difference. That would be the usual Calderon-Simon idea. So hopefully then we can use the usual Calderon-Simon idea, but we want to use it in an LP-LQ fashion. So that's again, in order to get the sharpest part of bounds, you want to use it in an LP-LQ, LP improving fashion. So with the previous approach in machinery, some boundary endpoint sparse bounds were obtained. And at the critical index, T-1/2, this was obtained by Conde Alonso, Culiu, Di Plinio, Anu. This can be seen as the extension of the Chris result, where remember that was weak type 1-1. So they proved this boundary edges all the way up, except for the 1-1 endpoint, which is unknown to the best of my knowledge. It's not decided whether it should be true or false. And then what happens away from this critical index for p equal to 1? Well, there's also another result. There's a result only in 2 dimensions by Kessler and Lacey. And then they prove that for any lambda, one can prove a boundary sparse bound, but not in the whole edge. Well, only if this was like small enough, I guess. But only for a partial boundary edge. And they left open what happens here in the remaining part, or also in the top line. And this was only done in dimension 2. Probably maybe that the reason was because that's where Bochner-Riesz is known, and then numerology is all the numerology is available. So then the result that the main result that I want to present is that we are able to close that gap in the work of Kessler and Lacey, and we are able to extend this to the whole vertical line, except for the upper end. And this would follow by duality, this horizontal region. So we are able to obtain that for all lambdas, that in 2 dimensions, and at that critical index. So that refines all the width type bounds. And also at the special case of lambda equals 1/6. And this is special because when then the secondary exponent becomes 2. So here we are here, this is Stein-Thomas becomes 2. And then we have extra orthogonality properties that allows us to obtain also this top boundary edge. But that we can only do it for the specific value of lambda, and we don't know yet how to do it in general. That's in 2 dimensions. But we also could prove something in higher dimensions. In this case, I'm not drawing the pictures, they would be analogous, but they wouldn't be for all lambdas, right? They would be only for the lambdas for which the Bochner-Riesz conjecture is known in higher dimensions, and then the numerology gets complicated. But what we prove is a black box type result, like tau did. So we have a conditional result that the same way that tau's result was relying on a vector value inequality, and he explained when to verify this vector value inequality. So we do the same thing. So now our inequality will no longer be a P inequality. It will be a P to Q. Here I wrote it in the way of P no to R. So it will be a P no to R, an off-diagonal vector value inequality. They already fit in width type bounds. Here we put an off-diagonal assumption. In that situation, then we prove the sparse bounds in the whole vertical segment. Okay. And then the question is, when does this inequality hold? So for which P does this hold? Well, always for Stein-Thomas. So at least in that regime, we can verify it. And then above from Stein-Thomas, we had to reprove. This is essentially the same argument as tau. So here there is no much contribution. This is just verifying that tau's theorem that was saying if Bochner-Riesz is bounded away from the endpoint, and Fourier restriction also holds for a specific P0, then we have this vector value inequality away from that P0, then the same thing continues to hold in an off-diagonal setup from LP to LR. Okay. So, so all in all, our theorem can be read in the following way. So assume that we have Bochner-Riesz LP to LR, LP0 to LR0 holds for all lambda in the openness, open values away from the critical index, and the Fourier restriction for the sphere maps LP0 to LR0, then we have a sparse bounds for the whole vertical segment. Okay, that's how our result reads. So once you have information on these problems, then sparse bounds now are for free. So let me now enter the second part of the talk, and let me elaborate on proof techniques. And here I'm gonna start from classical theory from Christ, see what the limitations are, present also the approach of Seeger, see what the limitations are when we try to push that to sparse bounds, and explain what we had to overcome. That's how I structured the talk. Because everything is quite technical, and that's the only way to understand where the difficulty is relying. So the ideas of Christ, well, he brought in an extension of the Calderon-Simon theory. So he brought fundamental new ideas by studying Bochner-Riesz at the critical index for P equal 1. And the issue with Bochner-Riesz is that it's a rougher kernel, and it doesn't satisfy the usual L1 to L1 estimate on the away from the exceptional set on the bad functions. It only satisfies a weak type estimate, and then weak types then are not good for triangle inequality. So one needs to improve the method of Calderon-Simon. And his idea was to bring in L1 to L2 estimates. So instead of proving an L1 to L1, if we prove an L1 to L2 with the right here with the power of lambda of alpha to compensate for the application of Chebyshev, which now we do come with alpha over 2. This divided by alpha over 2. When we apply Chebyshev, we need to divide everything by alpha over 2. So I need the alpha on top to end up with a L1 norm over alpha. So then we are good. And actually, because this is L2, so hopefully there's some orthogonality here, and we can just focus on a specific piece. So that was his idea. And as I mentioned at the beginning of the talk, his approach was based on decomposing the kernel on a spatial side. Remember, the kernel for large X is given by an oscillatory term divided by, here we are at the critical index for P equal 1, so we have the X to the power D in the denominator, which fails to be integrable by an epsilon, right? And this is why this becomes difficult, right? Plus some error terms, which we don't care about. So we decompose diagonally, and we maybe also need to do a finite partition of unity on the sphere. I'll explain it why. And we decompose on annuli. And once we decompose on annuli, this is amenable to arguments to play with the support properties. Like the operator is local at this scale, so let's try to see what happens when I act on this on the atoms and at other scales and so on and so forth. So so because we are aiming for an L2 estimate, there's going to be, we hope to use some orthogonality arguments. So the L2 estimate is going to involve a diagonal term and off-diagonal terms. So we'll need to know size estimates on convolutions of K with itself or with a reflection of itself and different Ks at different scales. And there are these estimates, which will come apparent in a second. And then what Christ's ideas were is like, okay, we're gonna group all the atoms at a specific scale. All the small ones, we put them together in B0. And then from the positive side length, I'll put all the ones at that level in one single function. And now we take the usual exceptional set in Calderon-Simon theory, which has control size by what we want, so we can focus on the complement. And if now I study what my kernel acting on the different, on all the bad functions, the sum over all else of the BLs, then I can decompose it into three terms: the B0, all the BLs up to matching the scale of the kit of the kernel, and all the ones that are larger than the scale of the kernel. Okay. So if I am larger, then convolving with the kernel, it doesn't really amplify the support, right? It doesn't make it any larger, only by a dilate by 2 or so. So then, because we focus on the exception, on the complement of the exceptional set, this is identically 0. So this term is not here. So we only need to focus on cubes which are strictly smaller than the scale for the kernel. So for the term B0, I'm going to start analyzing how the term B0 is. We want to estimate that in L2 norm. So I can throw in the kernel, the two kernels together, and hopefully use some regularized estimates by doing kernel convolved with kernel, like a TD starting. And then I trivially try to say, okay, L1, L infinity, and let's see what happens. And when I pointwise look at these estimates, we had here about for this guy, which was given precisely by this. And I have now the sum of all the cubes which are small. And the cubes are O of 1 at most. And then we are here at the scale 2 to the j. So we decompose dyadically, going from O of 1 to 2 to the j in the dyadic scales to the n. So then I can quantify this distance and pick up here that gain. And then we only look for each n of the cubes which are containing these angles. Right? And once we look at them, now here we can apply the stopping condition for our Calderon-Simon functions. Is controlled by alpha times the measure of the cube, but then all these cubes, they are containing this ring, right? So it's at most 2 to the m times d, and now I can sum, and I get a 2 to the j cancels out with this one, and I get some extra decay given by the lambda times the alpha. So I put this back into here, and we obtain what we wanted with an extra decay on j, and then I can sum this in j, so the term B0 is good. So the similar arguments also tells us that for fixed j, we can now, instead of doing B0 and Kj, we can also do Kj and Bj minus s. And before we were gaining 2 to the minus j lambda, now we gain the difference. So we gain 2 to the minus s lambda. So in the end, we want to sum in s. Here we have a double sum. But we also need to sum in j, right? So the sum in j, what we do is like a diagonal term, which is going to be these guys, and then another diagonal term. So for the diagonal term, we already did it. The other diagonal term, now we use the other smoothing estimates on these kernels, and we argue in a very similar way. And yeah, I won't spend any more time because I'm running short already. So we can close the argument. And how to obtain these crucial estimates, the crucial estimates on convolving. You can think of this capital L being the kernel, maybe rescale for convenience, but the kernel being Kj convolved with Kj tilde. And this is an oscillatory integral because this phase function is the cosine. This kata function with the cosine, so this is an oscillatory integral. One can verify that this has non-vanishing second derivatives, and therefore stationary phase gives you decay minus d minus 1 over 2 because we are in the sphere, and this precisely is the critical index for p equal 1. So this is where this lambda comes up back again by this stationary phase argument. So this was his ideas in a nutshell, was to use L2 bounds instead of L1 bounds, L1 to L2 bounds for Calderon-Simon ideas for both. So how to extend this to sparse bound. So here the contribution by Conde Alonso, Cooley, Di Plinio, and was that when I presented earlier on the method, here is an endpoint method, right? So we have this multi-scale setup. So remember, we had to understand inner products in the sparse category of bad functions. The bad functions, they were smaller than the scales for the kernel, remember, and then we have the B2 functions, right? So really it ends up being this very situation where we are looking at KJs acting on the bad functions at a smaller size than the J localization. And we wanted to get the summability. So Chris got that summability in S. So here's we're summing in J, but there's a sum in S outside. So we want to be able to sum in S. But we wanted to do it not in the L1 to L2 category. We want to do it in the L1 to L infinity category, because we want to get a sparse bound and we want to prove a 1-1 sparse bound or a 1-1 plus epsilon. So we want this exponent to be as close to 1 as possible. So in order to do that, then we need the estimate for the dual exponent for when Q is almost L infinity minus epsilon. So how to obtain this? How to go beyond Q equal to 2? So what they did was to basically interpolate Chris estimate with an exponent. Let's put almost infinity here. Let's put Q integer large enough. And when Q is integer, we can expand out. We can do like when Q is equal to 2, we have the diagonal terms. So here, let's expand out. We have this sum, all the possible sum for all parameters, and we have all these products, all these integrals, and so on and so forth. And then, because these kernels are localized, then in order for this to not be 0, then there should exist an x such that x is close to y, to this variable yi for the size of this kernel, and so on and so forth. So this is what I'm saying. In order for this not to be 0, then we need that these points they are all kind of like close to each other to some scale. So that allows us to essentially, when we think of the kernel size estimate, that allows us to, where this is about 2 to the minus JD, this allows us to get rid of the point x and just put here the variables y's. And once we are there, we have already won, because then we can integrate in the x variable. We can forget about that, and then we can integrate iteratively in the different y variables as if it was a iterated integrals. And then for each of the iterated integrals, for each of the one pieces, then this can be done in the very same argument as this type of Chris arguments where the cubes are containing to others, and so on. So essentially, one can close the argument without any gain in S, but we had the gain in S coming from the L2 argument. So then one interpolates, and then we get decay in the S parameter for Q as large as we want. Okay. So that was their contribution to realize we want to perform this argument. Then let's go now to look at Seeger's idea, because that's in the method in what Kessler and Lacey they based their sparse result. So Seeger's idea instead for the weak type estimate in 2 dimensions was based on decomposing the Bochner-Riesz operator, not on the kernel side, which is what Chris did, but on the multiplier side, following the classical decomposition of Cordova and Pfeffer. And here we decompose it on thin dyadic annuli that they approximate the unit sphere. In this context, he wanted now to prove weak type PP estimates. So the Calder-Rosimond decomposition was of the function f to the power p at height alpha to the p. And he considered BKs to be then considered the good functions, bad functions, consider the capital BKs the same as the same as in increased arguments, so the ones at the very same, all the cubes at the very same side length, and then one breaks the sum into the very same three pieces: the B0, smaller cubes, and large cubes. Okay, now in contrast to the previous case, large cubes now they matter, and they matter because this is a decomposition on the multiplier side, not on the kernel side. So we cannot do the kernel support argument to say that this term is always 0. So now this term actually also plays a role. So we need to study the three of them. So the goal is to obtain then these three estimates for the three terms. If one obtains these three estimates, then one closes the argument by Chebyshev when that's Calderon zero. Okay, we have this summability in S here. S is the distance between the scales of the operator and the cubes. Summability in sigma, where sigma is again the difference. And then for 0, we don't need any summability. Okay. How did he obtain that? And the key here was, as I mentioned at the beginning of the talk, to prove this type of vector valued estimate for Bochner-Riesz, or for the building blocks for Bochner-Riesz on the multiplier side. If we imagine that we have that this holds, and then let's see how to apply it to obtain these estimates. You can see that these estimates are already of some vector valued form, right? We have sum in J of TJs acting on some functions. So this is looking like this type of estimates. So if one has this, and then one applies this to 1 and 2 and 3, but one applies it to the R, then we are not going to get any gain in the S parameter, right? So we want to obtain that gain somewhere. So what we'll do is to do an analytic interpolation. So by analytic interpolation, we'll interpolate between a very large R that is admissible for our hypothesis in this vector valued estimate and 1. Okay, and here this would be the Bochner-Riesz index, the critical index. We interpolate between 1 and R. Okay, for when we are essentially at R, this is when the real part of the variable, interpolating variable is 1. Then we just apply the input vector valued estimate. We go from LR to LR, but then because of the way we are setting the interpolation up, this becomes the LP norm of BP because of this power here. We apply it to these functions, and then for when the real part is equal to 0, that means that we are like our operator is like Bochner-Riesz at the critical exponent p equal 1 and the critical index. So for p equal 1, we have trivial estimates for each piece, but we also have these L1 to L2 estimates by Christ, which come with by Christ and Saurabh when one looks at the multiplier decomposition, and they come with a decay. So then one interpolates this by Helder. We have L1 estimates, L2 estimate. One goes to LR estimate for the real part being 0, the other one for the real part being 1. One does analytic interpolation, and then one gets a result. So this is where it is key. The classical theory of Calderon-Simon-Christ, it's interpolated with this vector valued inequality. That's the input. And then the question is when the vector valued inequality is true, and then Seeger verifying 2 dimensions that's true by bilinear methods. So how does one extend that to sparse bounds? So Kessler and Lacey, they use the estimate, for instance, also for large cubes, but for simplicity, let's just focus on small cubes. So they use these estimates as a black box. We have this LP to LR estimate after doing this analytic interpolation that I mentioned, and so on and so forth. And we have it in this regime when P is smaller than R, smaller than 4/3. And really, in this argument, we should think that P is really like R. It's like R minus epsilon. That's what P is. So this has the constraint of having 4/3. So when one tries to run this into the sparse machinery argument, that gives you a P to R prime sparse bound. And this forces that the 1 over R prime exponent needs to be smaller than 1 over 4 because of these 4/3 here. So the dual exponent is 4 when the threshold for the dual exponent is 4, and therefore we have this constraint. And that's what Kessler and Lacey obtained. How one would be able to beat this restriction? So if you remember, we want to push this to be as high as possible. That's what as high as sparse bounds permit, right? And in particular, this optimal exponent would be that this number. I mean, again, why this number doesn't matter is like we want to get it tied to the optimal. So really, like let's try to think in the argument if there's anything that we could improve. So first of all, this estimate, as I said, was obtained for R being very close to P. That's how we should think of that. And this was by inputting an LR to LR vector valued inequality, which is the hypothesis. And then because of the complex interpolation, the way it's set up, the R on the right-hand side becomes a P. Okay. So what if instead of inputting an LP, little LP of LP to LP inequality, we try to input a little LR of LP to LR, an off-diagonal hypothesis, vector value. That would be one possibility to try to improve things. And the second one is that when we think of what happens at P equal 1, and we try to extend Green's method to sparse bound, the approach of Conde Alonso, Culiu, Di Plinio, and O was that the L1, L2 estimates, they are not good enough because that would have given us only sparse bounds for half the segment, not from between all the way down to 1, but between all the way up to only 1/2. That was what would have been. In order to go beyond 1/2 and go close to 1, one needs to go beyond 2 and goes close to infinity. And they did that by a localization argument. They look at the kernel was localized, and then they could play with the spatial localization of the kernel to push it up to L infinity minus epsilon. That's when I decompose the Q power into many multiple sums, and we did some estimates on the kernel. So there are these two things, that one input here, which should be maybe changed, and then we should try to implement this argument to make R as large as possible. It's not going to be infinity, but it's going to be this threshold. So let's try to push it up. The problem is that the last step that Conde, Culiu, Di Plinio, and U they used, this was relying on having a spatial localization of the kernel. And instead, this estimate is based on a Fourier multiplier decomposition. So the kernels are no longer long and compactly supported. These are two totally different decompositions. So how could we marry the two things in order to beat this exponent and be able to prove the sharp result? Okay, we need to merge the two arguments up. And then here, so this is the sum up. Okay, so maybe in case someone is lost, this, as I said, for P equal 1, the lambda D minus 1 over 2, the Chris decomposition later on kind of pushed to sparse bound by this group of people was all based on this kernel decomposition. The kernel decomposition in absolute value, they are L1 normalized kernels. Okay. And the rescale pieces, they are in L infinity, so therefore they go from L1 to L infinity. Right? That's the key. But the Kessler-Lacey, which is based on the Fourier multiplier decomposition, the corresponding kernels, they are not they don't have the right L infinity estimates or estimates for large exposure. They are not, they are different. Right? So let's try to marry the two. And there's and Chris actually tried to marry the two in a way, but the way he married the two, somehow it had a constraint. It has a constraint from 1 to the Stein Thomas exponent. So when we go back to Chris' original method, he didn't only prove the p equal 1 result, he was also able to extend it to Stein Thomas exponent away from this element. And then what he did again was what he did this earlier than Seeger. So the arguments I presented from Seeger, they come from here. He did the complex analytic interpolation and tried to prove this estimate. For now, we don't go to L1, we go to LP for P in this range, and we aim for an LP to L2 estimate with the right dependence here on alpha and the decay in S, summability in the difference of the scales. This is for small cubes. So he did analytic interpolation, and then what he did was to put on one end of the interpolation the L1, L2 estimate that he already had proven before. So he modifies so that the operator modifies in analytical interpolation, right? So because we modify the operator, when the real part is equal to 1, we set it up so that the operator is like the Bochner-Riesz for p equal 1 at the critical index, and then the L1 L2 estimate apply. They come with the epsilon, they come with the S gain, and then the L1 norm on the right becomes an LP norm just because we apply it to a different function. Okay, and what happens at the other end? So at the other end, he's interpolating that with a Stein Thomas estimate. So here, this would be the P0 here, would be the P0 coming from here, the Stein Thomas exponent. And in here, there is no gain in S. But if we interpolate, then we have gain in S in all the intermediate regions, and that's why we get the results in the intermediate range and not at the end. So, so his goal was to prove an LP0 to L2 Stein Thomas estimate. But the problem is that this is a decomposition on the kernel side. And in order to gain on L2 and take the sum outside, in order to use the orthogonality on the Fourier multiplier side that was given by the Cordova-Fetterman decomposition of that is automatic in that case, here is no longer automatic. So one needs to do something because we are decomposing on kernel and not on multiplier. So so then he decomposed dynamically the kernel, but he used a very special cutoff, like a trivial cutoff is not good enough. And the cutoff that he used was a cutoff that had this vanishing moment property for the Fourier transform of a function. So he managed to construct a function satisfying this property, and then he used that. This property here is only here is a vanishing moment, but only with respect to the first coordinate. And then he considered the dyadic decomposition and performed the decomposition of the kernel. So they have the same good properties in space. So the L1, L2 theory that he developed can be applied. And then with this, when he goes to the multiplier side, well, the first two conditions, they are nothing really. This is the right alpha is 0 is the right decay for the Bochner-Riesz. It really focuses on the unit ball, let's say, or away from the origin, right? And 3 and 4, they are the crucial. Okay. 3 and 4 is telling you it's in a neighborhood. It's in a neighborhood of the unit sphere 2 to the minus j, but this could still have a lot of overlap. They could have overlap, and then so this doesn't give me orthogonality because they all pile up. But how can we get something extra? So he used that vanishing moment condition to get get an improvement here, that they don't overlap fully. Both M and the derivative, they have here an extra gain when we are on the sphere. So if we were modulus of psi equal to 1, then this would give you a little gain. So this gives like a weak orthogonality property, and was useful for Stein-Thomas, but not beyond. Beyond, we would need more derivatives, not only the first two. And how he did this? Then he considered a partition of unity where he's putting 1 in the endpoints, and then the gain that he obtained when we are on the sphere, and then interpolate it smoothly to get some delta gain, and then divide by this cutoff, multiply and divide. Then by multiplying and dividing, then he did a Cauchy's bars, and when doing these Cauchy's bars, then this is in an infinity, and then he can take the sum outside. So he does a Cauchy's bars in the sum inside by having added this extra cutoff. So then he can take the sum outside, and then for each of the individual pieces, he applies Stein-Thomas. So our contribution was then, okay, let's try to improve that, because that only gives you as much as Stein-Thomas, but doesn't allow you to go beyond Stein-Thomas, because it's only giving you 2 derivatives. It's very tight to do these Cauchy's bars here. It's very tight to have 2. Let's try to go beyond and to not use Stein-Thomas. So then we look at Christ's expression, which was vanishing moments on a cutoff function. The vanishing moments, they were to respect to the one variable, only to one coordinate. So then instead, what we did was, let's consider the Bochner-Riesz function as a function of one dimension, because it's a function of modulus of psi. So let's consider it as a radial function, just one variable, and impose this vanishing moment condition just on one variable, and impose it for as many moments as we can, or as we wish. So then the hard work comes in constructing this. Okay, once we construct this, we then decompose the one-dimensional Fourier transform of the multiplier, of the Bochner-Riesz multiplier, dyadic. So we decompose that dyadically, and now we apply that to we apply that to our raw function being modulus of psi squared. And that gives us a decomposition of the original Bochner-Riesz multiplier. So this new decomposition, it essentially has the 2 properties that we wish, because it gives us that is essentially supported on the spatial annulus, and this will allow us to do the sort of Conde, Pouliot, Diplinio O argument, to push it up like all the way up to infinity. Let's say not to infinity, but to the right threshold for every exponent, for every value of lambda. But it allows you to go beyond Stein-Thomas, and this is essentially supported on the annulus as well. So it allows you to then implement the Seeger-Tau strategy of decomposing. It's almost like decomposing on the Fourier side, but retaining good spatial localizations. So these two, we could have these two properties. So then we could input the vector valued estimates coming from, let's say, a Fourier decomposition side to obtain the desired estimates for the right exponent R here, the R that should become optimal. Okay. So here, as I said, the key is that now we have the localization of the kernel to get the sharp range we have used. Okay, so let me just finish off by mentioning that the case Q equals 2, in here we can not only obtain this vertical up to the P2 and horizontal up to the P3, we can also obtain the P2 and the P3 and the middle range. This case is even more technical, but this is special because Q is equal to 2, so that now orthogonality can be exploited in a stronger way at this point. It's a little, sorry. The interpolation at the level of sparse bonds was not possible. So one would like to say, oh, if it holds at P2 and P3, then it also holds in the middle. But it's not possible. So we had to interpolate. We had to carry on the argument for sparse bonds and obtain all these estimates in between in the argument directly. Okay. But I'm not going to go into the details of that because the technicality increases. And so this is everything I want to say. So thank you for your attention.
Thank you, David, for a really nice talk. Are there any questions?
Hello. Hello. Hi. Can you please go back to the last page of the results? Not
Yeah.
the.
Yeah. So sorry, like the phone in my office is ringing 3 times, and this has disturbed me like for the last 2 minutes. Okay, I'll put it off. Okay. Yeah. Here you said
The last page of the results, not the ideas. In the middle of the talk.
sorry. Yeah. Here. Yeah.
Yeah. So do you know if you expect this to be true, that if m lambda is bounded, then the Fourier restriction should be bounded?
Okay. So
is redundant, yes.
Yeah. So if P0, if R0 is equal to P0,
okay,
that's the diagonal case, right? Okay. In that case, tau proof that this implies B.
Yes.
But B for R0 equal to P0, but not quite. It would imply for LP to LP for P strictly smaller than P0. So if the first one holds for R0 equal to P0, then it implies the second one for LP to LP for P strictly smaller than P0.
Okay, but not
that's Tau's original result. So here we don't know yet if A implies B, but we plan to look at that.
So I expect this to be true.
Ideally, yes. Maybe not at the critical line. So because this should also hold at the critical line, this estimate. Okay, when this is equal, this would be the this would be the endpoint. The endpoint restriction line would be 1 over R0 equals D plus 1 over D minus 1 over D0 prime. That would be the sharp restriction of the diagonal endpoint line. Okay. At that line, my suspicion is that we will not be, because these are, my suspicion is that we will not be able to prove that at that line, but maybe away from that line, yes.
So at that line, is R0 bigger than P0 at that critical line when you have equality?
So, okay, unfortunately, I don't have the iPad connected, but this line, you agree with me that is not present if I look from R0 to P0, right? I mean, this is just not present. Okay. Now we look at off-diagonal estimates, and the sharp of diagonal estimates would be when we have equality here. This is actually equal. Okay. For this Bochner-Riesz hypothesis, we don't need it. We just need this strict inequality for our conclusion. Okay. Okay. But it's not out of the question that this holds with equality.
I see.
If this, for instance, for Stein-Thomas exponents, it does hold with equality, right? When R0 is equal to 2. Okay. In that case, when it holds with equality, I suspect that it doesn't imply the restriction theorem with equality. We might lose the equality and we might only be able to get the strict. But in the open case, we might be able to get these also in the endpoint case. Does that make sense?
Yes. Yes. Thanks.
Okay, but this is exploration in progress. Let's say I cannot tell you
Understand.
yet, yes or not. It's in progress.
One more. So the ideas of Christ, right, having higher order moment vanishing, it does feel a lot like, to me, the proof sort of very similar to the proof of atomic decomposition for HP spaces for P less than 1. Am I correct in that? It has sort of similar flavor. Do you find the similarity, or is it completely different, or I'm just this is just nonsense?
I can't really tell you if it has a similar flavor, because I am not off the top of my head. I am now not. I don't immediately recall the exact proof that you are referring to, the construction for P is more than 1 of atomic spaces that you are mentioning. So I prefer not to give an answer which is inappropriate or inaccurate. Yeah.
Thank you very much.
Hello, sir. Could you go to the last slide of your?
Yes. There.
Yeah, this one. The last point you have written, sparse bound can't be interpolated. Do you mean that if you have 2 sparse forms, then even also you cannot interpolate 2 sparse forms into a single sparse form?
No, as far as I'm aware, there is no interpolation theory developed for sparse forms. So if we have that an operator is dominated in a bilinear form by like the usual inequality, like inner product of T of F1, F2, that's controlled in absolute value by a sparse form with 2 exponents, and also by a sparse form with another 2 exponents. As far as I'm concerned, there is no interpolation theory available for that, and I think it's not. I think it's also not possible. So then, if it were, then if I could prove this at P2, then automatically gives you all this region, right? Because the Bochner-Riesz is self-adjoint, so it would give me the P3, and then by interpolation would give me the P2 between the P2 and P3. But the sparse bounds can't be interpolated, to the best of my knowledge. So one needs to prove all this part directly. You see what I mean? So it's not enough to focus just on the P2. One needs to do the whole half line. Then the other half line can be done by duality, but this half line one needs to do it directly. So typically what one needs to interpolate somehow is some key inequality that features in the proof, let's say. So the proofs, there's going to be some input inequality that is the key. It might be a very complicated looking expression, but the idea is to when that can be interpolated, or what, for instance, here we have identified, these vector value inequalities are the key, right? These vector value inequalities, you can interpolate them, you can do things, but you cannot interpolate the resulting sparse bounds that they imply, right? So it's about identifying in the proof what are the more standard looking estimates, maybe very complicated to formulate, but standard looking because they are based on LP spaces that they can be interpolated. But the sparse bounds, as far as I'm concerned, they can't.
Yes, sir. Thank you.
Any more questions? So one last question. What about the maximal function for the Bochner-Riesz? Are there these kind of results available?
We have not looked at it, but I think it will be harder. I mean, the maximal function for Bochner-Riesz is already a very not well understood operator at the level of Lebesgue spaces. So that's as much as I can say.
If there are no more questions, let's thank David for a really nice talk once again.
Yeah, thanks. Thanks to the audience, and again, sorry for not being able to participate. Unfortunately, let me stop sharing because then maybe I can see the people in the audience a little bit bigger, because it just comes as very small in the Zoom.
Make
I don't. Oh, now I can make it bigger finally, and I just wanna see who's there and say hi to some familiar faces. Giuseppe is hi, and Professor Tangavelu as well. Yeah, and I think I saw Diogo on the other end. Yeah, so yeah, well, I'm sorry for having missed you, and also apologies for a very technical talk, online talk of 1 hour and a half, but hopefully it wasn't too painful. So thanks a lot for having me, and I wish you a very nice week. Well, a very nice 2 weeks, and a wonderful conference.
And wish you to a nice time ahead.
Yeah. Yeah, hopefully I can visit you some of the time. Yeah.
Sure. So before I sign out, I completely forgot there are some online audience also. Are there any questions from the online audience? No, just thanks. Okay, there are no questions. So thank you for your time. Thanks.
Yeah, no, thanks to you. Yeah. Thank you. Bye-bye.